Journal of Vision, 2004, 4, 13-21 http://journalofvision.org/4/1/213. Animal and human faces in natural scenes, how specific? To human faces is the N170 ERP component? Guillaume Rousselet. Centre de Recherche Cerveau and Cognition. Toulouse, France. Marc J. M. Mace. Centre de Recherche Cerveau and Cognition. Toulouse, France. Michel Fabre-Thorpe. Centre de Recherche Cerveau and Cognition. Toulouse, France. The N170 is an event-related potential component reported to be very sensitive to human face stimuli. This study investigated the specificity of the N170, as well as its sensitivity to inversion and task status when subjects had to categorize either human or animal faces in the context of upright and inverted natural scenes. A conspicuous N170 was recorded for both face categories. Pictures of animal faces were associated with a N170 of similar amplitude compared to pictures of human faces, but with delayed peak latency. Picture inversion enhanced N170 amplitude for human faces and delayed its peak for both human and animal faces. Finally, whether processed as targets or non-targets, depending on the task, both human and animal face N170 were identical. Thus, human faces in natural scenes elicit a clear but non-specific N170 that is not modulated by task status. What appears to be specific to human faces is the strength of the inversion effect. Keywords: N170, event-related potentials, rapid visual categorization, natural scenes, human faces, animal faces. Introduction. Several studies using event-related potentials, ERPs, have isolated a component, the N170, which appears to reflect a stage of visual processing at which objects are categorized. This component is a negative potential peaking at around 150 to 170 milliseconds over lateral occipito-temporal electrodes. It is generally larger and peaks earlier in response to human faces compared to many other object categories. Benton, Allison, Puce, Perez, and McCarthy, 1996, Carmel. And Benton, 2002, George, Evans, Fiore, Davidoff, and Wren. Alt, 1996, Roshan et al., 2000, Sajaf and Benton, 2001, Taylor, Edmonds, McCarthy, and Allison, 2001. The N170 is very sensitive to human faces, and some authors have suggested that it reflects their early structural encoding before face recognition processes take place, example Eimer, 1998. 2000a, Sajaf and Benton, 2001. However, these conclusions are drawn from experiments that have mainly used central presentations of isolated and homogeneous stimuli, with the exception of Eimer, 2000b, example who used peripheral presentations. Here we report the results from an experiment in which we investigated whether a N170 can be found for faces in the more realistic context of natural scenes. To this end, subjects were requested to categorize as fast and as accurately as possible human faces in briefly flashed photographs of natural scenes. For comparison, they performed a control task in which they had to categorize animal faces under the same conditions. According to previous reports, a N170 of larger amplitude was expected in response to human faces compared to animal faces. The N170 has also been found to be particularly affected by face inversion, contrary to other object categories. It is delayed for inverted faces compared to upright faces. Benton et al., 1996, Eimer, 2000c, Ideer and Taylor, 2002. Reba, Poirou, Bernard, and Lalonde, 2001, Roshan et al. 1999, Roshan et al., 2000. It is also delayed for faces with eyes removed, Eimer, 1998, during the analysis of single face components, Benton et al., 1996, Gemmell, George. Chabi, Fiore, and Renault, 1999, or when attention is direct to alphanumeric strings superimposed on the center of the face, Eimer, 2000c. N170 amplitude has been found to be larger in response to inverted than upright faces, Ideer and Taylor, 2002, Roshan et al., 1999, 2000, Sajaf and Ben Tin, 2001. In relation with the behavioral literature, the effects of inversion on the N170 have been interpreted as reflecting the disruption of processing of the spatial relationships between face components, configural information. See more details in Ideer and Taylor, 2002, Moorer, L.E. Grand, and Mondlock, 2002, Roshan and Gautier, 2002. Hence, normal face perception would rely on mechanisms dedicated to the processing of upright face configural information. However, an enhancement of N170 amplitude has also been found for inverted houses, Eimer, 2000c. And various categories of real-world objects, Ideer, Latinus, and Taylor, 2003, and an increase in latency has been reported for inverted cars and words, Roshan, Joyce, Cottrell, and Tar, 2003, suggesting that the inversion effect DOI 10.1167/4.1.2 received May 15, 2003, published January 30, 2004 ISSN 1534-7362 Copyright 2004 Arvo. Journal of Vision, 2004, 4, 13-21 Rousselet, Mace, and Fabre-Thorpe 14. Might not be face-specific, unlike results found by Roshan et al., 2000. In this study, we wanted to determine whether an inversion effect would occur with human and animal faces in natural scenes. To address this issue, half of the pictures were presented in an upright position, the other half were presented upside down. According to some previous reports, Benton et al., 1996, Dahan, Pascalis, and John Sun, 2002, Reba et al., 2001, Roshan et al., 2000, an inversion effect was expected on the N170 for pictures containing a human face but not for those containing an animal face. However, a small inversion effect in response to animal faces was also possible given those found for various object categories, Eimer, 2000c, Ideer et al., 2003, Roshan et al., 2003. Finally, there is a controversy in the literature about whether the N170 can be modulated by task requirements. For example, when faces are given a target task status versus a non-target task status. Among the few studies that investigated this aspect, some have reported that the N170 does not seem to be modulated by task requirements, Carmel and Benton, 2002, Severac-Cockhill, Edmonds, and Taylor, 2000. However, top-down effects have also been reported on the N170, indicating that the neural mechanisms indexed by the N170 are not totally immune from high-level control. Benton and Golland, 2002, Benton, Sajev, Mecklinger, and von Kramen, 2002, Eimer, 2000b, 2000c. To investigate this issue in the present experiment, targets of a given task were used as non-targets in the other task. For example, when subjects performed the human face categorization task, half of the non-targets were pictures of animal faces, and vice versa. We were thus able to compare the N170 elicited by a given category of faces when processed either as target or as non-target. To summarize, the present study was designed to assess the specificity of the N170 for human faces in natural scenes as well as its sensitivity to inversion and to task status in such a context. Methods. Participants. 24 participants were tested, 12 women and 12 men, mean age 30 years, ranging from 19 to 51 years, 3 of them were left-handed. They volunteered in the study and gave their written informed consent. All participants had normal or corrected to normal vision. Experimental procedure. Subjects sat in a dimly lit room at 100 centimeters from a computer screen, resolution, 800 x 600 pixels, vertical refresh rate, 75 Hz, controlled by a PC computer. To start a block of trials, they had to place their finger on a response pad for 1 second. A trial was organized as follows: a fixation cross, 0.1 degrees of visual angle, appeared for a 300 to 900 milliseconds random duration and was immediately followed by the stimulus. Presented for 2 frames, i.e., about 23 milliseconds in the middle of the screen. Participants had to lift their finger as quickly and as accurately as possible, go response, each time a target was presented. Responses were detected using infrared diodes. Subjects had 1000 milliseconds to lift their finger, after which their response was considered a no-go response. A black screen remained for 300 milliseconds following this maximum response time delay, before the fixation point was presented again for a variable duration, resulting in a random 1600 to 2200 milliseconds intertrial interval. When the photographs contained no target, subjects had to keep their finger on the pad for at least 1000 milliseconds, no-go response. Subjects alternated between 2 categorization tasks: processing either human faces or animal faces as targets. They were asked to respond as fast as possible while minimizing errors. Each task consisted of 1 block of 4 consecutive series of 96 trials each. Half of the subjects performed the human face task first, while the other half started with the animal face task. Before each task, subjects were given a 48 trial training session. All series of pictures, figure 1, contained 50% targets and 50% non-targets. Among non-targets, half were neutral non-targets that had to be processed as such in both tasks, and half were targets of the other task, i.e., human faces. When subjects performed the animal face task and animal faces when they performed the human face task. Moreover, half of the images for each condition were presented upright while the other half were presented upside down. Rotation 180 degrees. A given subject saw each image only once, with 1 orientation, upright or inverted, and 1 status, target or non-target, but the design was counterbalanced for all conditions across the set of subjects to allow all data comparisons without any bias over the group of subjects or the sets of images. Stimuli. We used photographs of natural scenes taken from a large commercial CD-ROM library, Corel Stock Photoli. Libraries 1 and 2, example see Figure 1. All photographs were horizontal, 768 times 512 pixels, sustaining about 19.8 degrees by 13.5 degrees of visual angle, and chosen to be as varied as possible. Animals included mammals, birds, fish, and reptiles. Man faces included Caucasian and non-Caucasian people. Animal and human faces were shown as close-ups in reales. Tick conditions. The pictures could show more than one face. And the faces were not necessarily centered. There was a very wide range of non-target images, neutral non-targets. That included outdoor and indoor scenes, natural landscapes, street scenes, pictures of food, fruits, vegetables, plants, buildings, tools, and other man-made objects, as well as some more tricky non-targets, example dolls, sculptures, statues, and a few non-target images containing humans for which the faces were not visible in a given task, together with non-targets that were targets of the other task. These more ambiguous non-targets were used to assess the SOPHIES. Journal of Vision, 2004, 4, 13-21 Rousselet, Mace, and Fabre-Thorpe 15. Tication of the behavioral responses triggered in our FAST categorization task. See Rousselet, Mace, and Fabre-Thorpe. 2003, for further discussion on this point. Subjects had no a priori information about the press. Hints, the size, the position, or the number of targets in an image. Unique image presentation prevented learning. Evoked potential recording and analysis. Brain electrical activity was recorded from 32 electrodes. Mounted in an elastic cap in accordance with the 10-20 system, Oxford Instruments, with the addition of extra occipital electrodes, using a synapse amplifier system, new Riscan. The ground electrode was placed along the mid-line, ahead of FZ, and impedances were systematically kept. Below 5K signals were digitized at a sampling rate of 1000 Hz, corresponding to a sample bin of 1 millisecond, and low pass filtered at 100 Hz. Potentials were referenced online to the CZ electrode and averaged referenced offline. Base line correction was performed using the 100 milliseconds of pre-stimulus activity. 2 artifact rejections were applied over the 100 ms plus 400 milliseconds time period, first on frontal electrodes with a criterion of 80 plus ADV to reject trials with eye movements, and second on parietal electrodes with a criterion of 40 plus 40V to remove trials with excessive activity in the alpha range. Subjects were asked to minimize eye movements. Only correct trials were averaged. ERP components were low-pass filtered at 40 Hz before analysis. Targets non-targets. Human face task. Human faces animal faces neutral non-targets. Animal face task. Human faces animal faces neutral non-targets. Figure 1. Examples of human, animal, and neutral non-target pictures used in the human face and the animal face categorization tasks. ERPs were computed separately for correct target trials and correct non-target trials. We report results for the N170 at 6 temporo-occipital electrodes where its amplitude was maximal, left hemisphere, T5, O1, CB1, right hemisphere, T6, O2, CB2. Note that CB1, CB2 are referred as PO9, PO10 in the 10-10 system. For each experimental condition and each hemisphere, the peak latency was taken. from the electrode that presented the highest peak amplitude. Amplitude was then measured at that latency for the remaining electrodes, picked in ETAL, 2000. Peak amplitudes and latencies were entered into Omnibus ANOVA with task status, target versus non-target, category, human face vs. animal face, orientation, upright versus inverted, hemisphere, left versus right, and electrode, 3 levels, only for amplitudes. As within subject factors. To compare the neutral non-target. Journal of Vision, 2004, 4, 13-21 Rousselet, Mace, and Fabre-Thorpe 16. Amplitude, V, latency, ms, N170 to the N170 associated with human and animal faces. Seen as non-targets, a non-target factor, neutral non-targets versus non-target faces, was used instead of the task status FAC. Tour. Greenhouse Geyser corrections were applied and post-hoc t-tests were performed with a Bonferroni correction. Left-right left-right. Up animal faces as targets -2.3. 0.7. -4.2. 0.6. 176. 3.3. 174. 2.5. INV animal faces as targets -2.5. 0.6. -4.3. 0.5. 177. 3.3. 178. 2.4. Up animal faces as non-targets. -2.2. 0.6. -4.3. 0.5. 177. 3.2. 176. 2.6. Results. INV animal faces as non-targets. -2.4. 0.6. -4.2. 0.5. 178. 3.2. 180. 2.4. The behavioral results associated with this experiment have been presented in a previous article, Rousselet et al. 2003, Experiment 2. Overall, very good performances were found in the human and in the animal task, which hardly differed from one another. The close similarity of behavioral results makes the ERP for these two categories perfectly comparable. Up human faces as targets -1.9. 0.6. -3.8. 0.5. 168. 3.4. 169. 2.2. INV human faces as targets -3.0. 0.6. -5.7. 0.5. 173. 3.4. 174. 2.4. Up human faces as non-targets. -1.7. 0.6. -3.6. 0.5. 168. 3.0. 169. 2.7. INV human faces as non-targets. -2.9. 0.6. -5.3. 0.5. 176. 3.0. 175. 2.3. Up neutral non-targets 0.3. 0.6. -0.6. 0.4. 172. 3.5. 173. 2.7. N170 in natural scenes, specificity and effect. Of task requirement. INV neutral non-targets minus 0.3, 0.6, minus 1.2, 0.5, 173, 3.4, 176. 2.6. The most important result from these analyses is the finding of a large N170 in response to all faces in natural scenes, Figure 2 and Table 1. Its amplitude was much larger than the one recorded for very varied control natural scenes, confirming the sensitivity of the N170 to facial features, Figure 2b. In addition, the N170 was not modulated by task requirement, Figure 3. Table 1. Summary of N170 mean peak amplitudes and latencies. Results are reported for each hemisphere separately and values were averaged over the 3 electrode sites from which the peaks were measured. SE is indicated in brackets. Up equals upright, INV equals inverted. A clear N170 was recorded following the presentation of upright human and animal faces when seen as targets. Upright target human faces. 200. 4V. 2. 0. Minus 2. 100 300 400. MS. Minus 6. Minus 4. 200. 4. 2. 0. Minus 2. 100 300 400. Minus 6. Minus 4. P1. N170 upright non-target human faces. Upright non-target animal faces. Upright neutral non-targets. 200. 4. 2. 0. Minus 2. 100 300 400. Minus 6. Minus 4. 200. 4. 2. 0. Minus 2. 100 300 400. Minus 6. Minus 4. A. B. Upright target animal faces. Figure 2. N170 specificity. Grand averages across 24 subjects showing the N170 at electrodes T5, left, and T6, right, where it had the largest amplitude. A N170 associated with the presentation of upright human and animal faces seen as targets. B N170 associated with the presentation of upright neutral non-targets and upright human and animal faces seen as non-targets. Note that the N170 was preceded by a large P1 component. Results for this component are not reported in this work. Journal of Vision, 2004, 4, 13-21 Rousselet, Mace, and Fabre-Thorpe 17. Figure 2a and Table 1. The N170 amplitudes in these two conditions did not differ significantly from one another. F 1 23 equals 3.1, P equals 0.09, although the N174 animal faces was on average 0.4 V plus / 0.25 V, SE, larger than the N170 for human faces, Figure 2a. The N170 latency was 6 milliseconds plus / 1.3 milliseconds shorter for human than on a mal upright targets, F 1 23 equals 23.0, P.0001. No significant effect of task status was seen on either N170 peak amplitude, F 1 23 equals 2.9, P equals 0.10, or latency, F 1 23 equals 2.0. P equals 0.17, Figure 3. Thus, the same effects reported for upright target faces were also found for upright non-target faces, Figure 2b and Table 1. There was a non-significantly Larger N170 amplitude for animal faces compared to man faces seen as non-targets, difference equals 0.6 V plus slash 0.3 V, F, 1,23, equals 3.3, P equals 0.08, figure 2b, while N170 latency was 8 milliseconds plus slash 1.2 milliseconds shorter for human than for animal. Pictures, F, 1, 23, equals 48.1, P .0001. The N170 elicited by human and animal faces when seen as non-targets was 2.9 V plus slash 0.2 V larger than the one recorded in response to neutral non-targets, figure 2b. And table 1, as shown by a significant amplitude effect between human and animal face N170 and neutral non-target N170, F, 1, 23, equals 211.7, P .0001. This effect was stronger over right, difference equals 3.5 V plus slash 0.3 V, then left, 2.3 V plus slash 0.2 V, hemisphere electrodes, F, 1, 23, equals 9.8, P equals 0.005. The neutral non-target N170 was significantly more prominent at sites T5 T6, on average plus 1.9 V. Plus slash 0.4 V compared to O1 O2 and CB1 CB2, F, 2, 46. Equals 21.0, P .0001. Upright human and animal faces, whether seen as targets or non-targets, were associated with a larger N170 at sites CB1 CB2 and T5 T6, difference equals 2.4 V plus slash 0.3 V compared to O1 O2, F, 1.8, 40.3, equals 24.7. P .0001, with a non-significantly larger amplitude OB, served at T5 T6 relatively to CB1 CB2. In addition, the N170 amplitude in these conditions was larger over right hemisphere electrodes, difference equals 2 V plus slash 0.6 V, F, 1, 23, equals 9.7, P equals 0.005. Effects of inversion on the N170. The effect of inversion was studied on animal faces and human faces seen both as targets or non-targets and on neutral non-targets that did not contain any face. When human and animal faces were compared, the N170 amplitude was enhanced by inversion of both targets and non-targets, but this effect was restricted to human pictures as shown by a significant interaction between category and orientation factors, F, 1, 23, equals 33.5, P. No amplitude effect was observed for animal faces, F, 1, 23, equals 0.5, P equals 0.5, figure 4b. This interaction also means that the N170 was on average larger in response to inverted human faces than inverted animal faces, difference equals 0.9 V plus slash 0.2 V. The latency of the N170 peak was shorter for upright than for inverted faces, a result that again was not affected by task status, F, 1, 23, equals 56.3, P .0001, figure 4a and 4b. An interaction between category and orientation FAC. Tours, F, 1, 23, equals 7.2, P equals 0.013, revealed that this effect was 200. 4V. 2. 0. Minus 2. Minus 4. Minus 6. 100 300 400. MS. Upright animal faces. Target trials. Non-target trials. 200. Upright human faces. 4. 2. 0. -2. -4. -6. 100 300 400 200. 4. 2. 0. -2. -4. -6. 100 300 400. 200. 4. 2. 0. -2. -4. -6. 100 300 400. Figure 3. Task status effect. Grand averages across 24 subjects showing the N170 at T5, left, and T6, right, sites for correct trials. ERP components following the presentation of a given category with a target and a non-target task status are compared. Journal of Vision, 2004, 4, 13-21 Rousselet, Mace, and Fabre-Thorpe 18. Upright target animal faces. Inverted target animal faces. Upright target human faces. Inverted target human faces. 200. 4. 2. 0. -2. 100 300 400. -6. -4. 200. 4. 2. 0. -2. 100 300 400. -6. -4. 200. 4. 2. 0. -2. 100 300 400. -6. -4. 200. 4v. 2. 0. -2. 100 300 400. ms. -6. -4. c. Upright neutral non-targets. Inverted neutral non-targets. 200. 4. 2. 0. -2. 100 300 400. -6. -4. b. 200. 4. 2. 0. -2. 100 300 400. -6. -4. a. Figure 4. Inversion effect. Grand averages across 24 subjects showing the N170 at T5, left, and T6, right, sites for correct trials. ERPs. Following the presentation of upright and inverted pictures are compared separately for human targets, A, animal targets, B, and new trial non-targets, C. ERPs for human and animal faces processed as non-targets are not shown because they were associated with the same N170 effects. Stronger for human faces, +6 milliseconds +/1 millisecond, target human faces, f1, 23, equals 16.7, p.0001, then for animals, +3 milliseconds +/1. ms, target animal faces, f1, 23, equals 7.1, p equals 0.01, non-target. Animal faces, f1, 23, equals 6.7, p equals 0.02, figure 4, regardless of whether they were seen as targets or as non-targets. We also analyzed the N170 for upright and inverted neutral non-targets, figure 4c. There was no effect of inversion on the latency of the neutral non-target N170, f1. 23, equals 1.5, p equals 0.2. Surprisingly, its amplitude was significantly enhanced by inversion, plus 0.6 v +/0.2 v, f1. 23, equals 6.3, p equals 0.002, but to a lesser extent than for the man face N170, significant interaction between non-target category and orientation factors, f. 1, 23, equals 15.4, p equals 0.001. Discussion. This study was aimed at analyzing the N170 recorded in response to human and animal faces in upright and invert natural scenes. The main results are the following. 1. It is shown for the first time that there is a clear N170 component for faces of very different kinds presented in the context of natural scenes. 2. Extending the results from some previous reports. The N170 does not appear to be specific to human faces, being here of similar amplitude in response to a large set of animal faces. 3. Strong inversion effect that increased both the N170 latency and its amplitude was seen in response to human faces. With other stimuli, the inversion effect was reduced and restricted to the amplitude effect with neutral non-targets and to the latency effect with animal faces. Journal of Vision, 2004, 4, 13-21 Rousselet, Mace, and Fabre-Thorpe 19. These 2 points confirm results from some earlier studies and suggest that what appears to be specific to human faces is not the N170 or the inversion effect, but rather the strength of the inversion effect. 4. Confirming some previous findings, the N170 recorded in response to human faces does not appear to be affected by task status. This result is here extended to animal faces. Although a definitive conclusion about this null effect is premature, it could reflect the fact that, compared to other objects, faces are processed by default up to a higher level of representation without requiring specific attention. The presentation of close-up views of human faces in the context of natural scenes was associated with a clear N170. The amplitude of the signal was much larger than the one recorded following the presentation of a large range of control scenes containing various kinds of objects. Thus it appears that there is a N170 effect even in the context of natural scenes. This larger amplitude in response to human faces compared to control objects has been used as the hallmark of the N170 face specificity, example Benton et al., 1996. However, the N170 recorded in the present experiment did not appear to be specific to human faces. Indeed, its amplitude was not different from the one recorded in response to animal faces. This means that the N170 itself is not specific to human face features as already stated previously by others, Roshan et al., 2000. However, the N170 presented a maximum earlier for human faces compared to animal faces. In previous experiments, the N170 has been reported to be either larger and delayed, Dahan et al. 2002, or just delayed, Carmel and Benton, 2002, following the presentation of upright monkey and ape faces, respectively. Because delayed and enhanced N170 have been taken as evidence for the disruption of configural mechanisms dedicated to the processing of upright faces, Eimer, 2000a, Ideer and Taylor, 2002, Roshan et al., 1999, Dahan et al., 2002, postulated that monkey faces were somehow equivalent to inverted human faces, disturbing the canonical human face configuration. On the other hand, Carmel and Benton, 2002, concluded that the N170 reflects the involvement of a mechanism triggered by every stimulus, sharing the same spatial organization as a human face. The results from the present study indicate that this spatial Ganization might be relatively coarse, including facial char. Characteristics from very various kinds of animals seen from different viewing angles. The shorter N170 latency in response to human faces might also be taken as evidence for a sensitivity of this component to the precise configuration of the human face. Carmel and Benton 2002, see also Eimer, 1998, 2000a. In this context, a delayed N170 for animal faces would imply a delayed analysis of their features and their spatial relations. However, the difference in peak latency between the two categories, although highly significant, was very limited, 6 to 8 ms. Furthermore, human and animal faces in this study were processed at the same speed according to behavioral data, Rousselet et al., 2003. Thus, a very simple explanation cannot be ruled out, namely that this delay would be due to a higher variability in animal pictures. All kinds of vertebrates were used, compared to more homogeneous human pictures. As a result of the averaging process by which ERPs were computed, this might be reflected in a slightly delayed N170 peak latency for animal face pictures compared to human face pictures. Although the present results do not support the hypothesis that the N170 is specific to human faces, the strength of the inversion effect was quite specific to human face pictures. Indeed, although inversion of animal faces and neutral non-targets increased the latency and the amplitude of the N170, respectively, these effects were of much smaller magnitude than those found for human faces. Thus, even if there is growing evidence for the existence of N170 inversion effects for stimuli other than human faces, Eimer, 2000c, Idier et al., 2003, Roshan, Gautier, Gaffo, Tar, and Cromlink, 2002, Roshan, et al., 2003, a systematic inversion effect of large amplitude seems to be the hallmark of human faces. The larger N170 amplitude with inversion might be due to inverted faces recruiting additional population of neurons with broader selectivity compared to upright faces that would activate only face-selective neurons, Roshan et al., 1999. On the other hand, recent studies by Idier and Taylor, 2004, and Watanabe, Kakaji, and Puce, 2003, suggest that upright and inverted faces activate the same areas, but with a slower time course in the last case. These authors also conclude that areas in the lateral temporal cortex, around the superior temporal sulcus, are important generators of the N170. Furthermore, the location of the electrodes recording maximal N170, such as T5 T6 in the present experiment, is optimal to capture the activity of those brain areas, Benton et al., 1996. Given the functional properties of these lateral cortical areas, Allison, Puce, and McCarthy, 2000, the N170 might be linked to the process of eye gaze, as well as face expression, emotion, and other biological cues. Now, one can hold the plausible assumption that by default this lateral network would find an attractor corresponding to one or a combination of those properties. Thus, from a computational point of view, the larger N170 amplitude with inversion might be due to the massive recruitment of collaterals in an auto-associative network trying to find a stable attractor. The weak inversion effect for objects might be explained by the relative specificity of this network to human faces. One can also advance the hypothesis that the presence of eyes in animal faces might be sufficient to produce a large N170, in keeping with data suggesting that the N170 is in part an automatic response to eyes, Benton et al., 1996, SCHYNS. Jensch, Johnson, Schweinberger, and Goslin, 2003, but C. Eimer, 1998. Surprisingly, despite a larger inversion effect for human faces compared to animal faces, the behavioral results associated with these two categories revealed a similar drop in Journal of Vision, 2004, 4, 13-21 Rousselet, Mace, and Fabre-Thorpe 20. Accuracy, 0.6%/0.3%, respectively, and mean reaction times, +14 ms/+10 ms, respectively, with inverted stimuli. Rousselet et al., 2003. Further investigations will be necessary to establish the relationship between the N170 and the behavioral performance in face categorization tasks. Another interesting result reported here is the absence of an effect of task status on the N170 for either human or animal faces. This might be taken as evidence that, by default, faces are processed to a high level of representation, whether or not they are pertinent for the ongoing activity. Tanaka, 2001. The absence of task status on the N170 is in keeping with previous reports that explored the effects of top-down processing on face ERP, Carmel and Benton, 2002. Severak-Cockhill et al., 2000, and Cepius, Allison and McCarthy, 1999, for intracranial recordings. However, it contradicts other findings showing that task requirements can modulate the N170, Eimer, 2000b, 2000c, Benton and Galland, 2002, Benton et al., 2002. The absence of task status effect on the N170 in the present study might find its origin in the relative simplicity of the tasks employed. Indeed, behavioral results, Rousselet et al., 2003, indicate that human subjects are fast and especially accurate at categorizing faces and animals in natural scenes. On the contrary, Eimer found effects related to task status when using demanding comparison tasks, Eimer, 2000b, and a difficult detection task of red digits superimposed on black and white faces, Eimer, 2000c. Thus, the N170 modulation linked to the status of faces in various tasks might be correlated to specific requirements and may be observed only when face processing needs to reach a high level of detailed visual analysis. These results seem to be at odds with previous reports showing that animals and other targets can start to be discriminate at about 150 milliseconds in natural images, Thorpe, Fies, and Marlett, 1996, Van Rollen and Thorpe, 2001. In the present experiment, the first task status effects were found at about 170 milliseconds for human faces and even later, around 230 milliseconds, for animal faces, Rousselet, Mace, Thorpe, and Fabre-Thorpe, 2003. However, when a given category seen as target was compared to the other category seen as non-target, both human and animal faces were associated with early effects with onsets as short as 120 to 140 milliseconds. Moreover, the onset latencies of these early ERP effects might be related to the subject's reaction times, contrary to what was reported recently by Johnson and Olshausen, 2003. Thus, although the visual system might be able to start to discriminate very early between animal and human faces might be processed by default to a higher level of representation such that the associated ERPs are not modulated easily by task status. Acknowledgements. We thank Naj M. Bacon-Mace for her help in programming image presentation and Anne-Sophie Paroisian for her help testing subjects. This manuscript was improved by discussions with Roxana J. Itier. This work was supported by the grant ACI Cognitici and degree IC2. Financial support was provided to GARNM.JM. Mace by a Ph.D. grant from the French government. Commercial relationships, none. Corresponding author, Guillaume Rousselet. Address, Department of Psychology, McMaster University, Hamilton, On, Canada. Email, rouseg@universitymail.sys.mcmaster.ca. References. Allison, T., Puce, A., and McCarthy, G. 2000. Social perception from visual cues, role of the STS region. Trends in Cognitive Sciences, 4, 7, 267 to 278. PubMed. Benton, S., Allison, T., Puce, A., Perez, E., and McCarthy, G. 1996. Electrophysiological Studies of Face Perception in Humans. Journal of Cognitive Neuroscience, 8, 551. 565. Benton, S., and Golland, Y. 2002. Meaningful Processing of Meaningless Stimuli, the Influence of Perceptual Experience on Early Visual Processing of Faces. Cognition. 86, 1, B1-14. PubMed. Benton, S., Sajev, N., Mecklinger, A., Friederici, A., and von Kramen, Y.D. 2002. Priming Visual Face Processing. Mechanisms, Electrophysiological Evidence. Psychology. Cal Science, 13, 2, 190 to 193. PubMed. Carmel, D., and Benton, S. 2002. Domain Specificity versus Expertise, Factors Influencing Distinct Processing of Faces. Cognition, 83, 1, 1-29. PubMed. DeHaan, M., Pascalis, O., and Johnson, M. 2002. Specialization of neural mechanisms underlying face recognition in human infants. Journal of Cognitive Neuroscience. 14, 2, 199 to 209. PubMed. Eimer, M. 1998. Does the face-specific N170 component reflect the activity of a specialized eye processor? New. Rohrport, 9, 13, 2945 to 2948. PubMed. Eimer, M. 2000A. The face-specific N170 component reflects late stages in the structural encoding of faces. Neuroreport, 11, 10, 2319 to 2324. PubMed. Eimer, M. 2000B. Attentional modulations of event-related brain potentials sensitive to faces. Cognitive Neuropsychology, 17, 1/2/3, 103 to 116. Eimer, M. 2000C. Effects of face inversion on the structural encoding and recognition of faces, evidence from event-related brain potentials. Cognitive Brain Research, 10, 1 to 2, 145 to 158. PubMed. George, N. Evans, J. Fiore, N. Davidoff, J. and Renault, B. 1996. Brain events related to normal and moderately scrambled faces. Cognitive Brain Research, 4, 2, 65 to 76. PubMed. Journal of Vision, 2004, 4, 13 to 21. Rousselet, Mace, and Fabre-Thorpe 21. Ideer, R.J., Latinus, M., and Taylor, M.J. 2003. Effects of inversion, contrast reversal and their conjunction on face, eye, and object processing, an ERP study. Journal of Cognitive Neuroscience, D292, 154. Ideer, R.J., and Taylor, M.J. 2002. Inversion and contrast. Polarity reversal affect both encoding and recognition processes of unfamiliar faces, a repetition study using ERPs. Neuroimage, 15, 2, 353 to 372. PubMed. Ideer, R.J., and Taylor, M.J. 2004. N170 or N1. Spatio. Temporal differences between object and face process. Using ERPs. Cerebral cortex, 14, 2, 132 to 142. PubMed. Gemmell, B., George, N., Chabi, L., Fiore, N., and Renault, B. 1999. Differential processing of part-to-whole and part-to-part face priming, an ERP study. Neuroreport. 10, 5, 1069 to 1075. PubMed. Johnson, J.S., and Olshausen, B.A. 2003. Time course of Neural Signatures of Object Recognition. Journal of 6. Zion, 3, 499 to 512, http://journalofvision.org/3/7/4. doi 10.1167/3.7.4. PubMed article. Maurer, D., Legrand, R., and Mondlock, C.J. 2002. The Many Faces of Configural Processing. Trends in Cognitive Sciences, 6, 255 to 260. PubMed. Picton, T.W., Benton, S., Berg, P., Duncan, E., Hilliard. S.A., Johnson, R., Jr., et al. 2000. Guidelines for Us. Human Event-Related Potentials to Study Cognition. Recording Standards and Publication Criteria. Psycho. Physiology, 37, 2, 127 to 152. PubMed. Puce, A., Allison, T., and McCarthy, G. 1999. Electro. Physiological Studies of Human Face Perception. 3, F. Effects of top-down processing on face-specific potent tiles. Cerebral cortex, 9, 5, 445 to 458. PubMed. Reba, M., Poirou, S., Bernard, C., and Lalonde, R. 2001. Event-related potentials for category-specific informa. During passive viewing of faces and objects. Inter. National Journal of Neuroscience, 106, 3 to 4, 209 to 226. PubMed. Roshan, B., Delvenet, J.F., Debatis, D., Goffo, V. Breuer, R., Cromlink, M., and Garrett, J. M. 1999. Spatiotemporal localization of the face inversion F. Effect, an event-related potential study. Biological Psychology, 50, 3, 173-189. PubMed. Roshan, B., and Gautier, I. 2002. How does the brain process upright and inverted faces? Behavioral and Cognitive Neuroscience Reviews, 1, 62-74. Roshan, B., Gautier, I., Gaffo, V., Tar, M.J., and Cromlink, M. 2002. Expertise training with novel objects leads to left lateralized face-like electro-physiological responses. Psychological Science, 13, 3. 250-257. PubMed. Roshan, B., Gautier, I., Tar, M.J., Despland, P., Breuer, R., Leenot, S., and Cromlink, M. 2000. The N170 occipitotemporal component is delayed and enhanced to inverted faces but not to inverted objects, an electrophysiological account of face-specific processes in the human brain. Neuro Report, 11, 69-74. PubMed. Roshan, B., Joyce, C.A., Cottrell, G.W., and Tar, M.J. 2003. Early lateralization and orientation tuning for face, word, and object processing in the visual cortex. Neuroimage, 23, 1609-1624. PubMed. Rousselet, G.A., Mace, M.J.M., and Faber-Thorpe, M. 2003. Is it an animal? Is it a human face? Fast PROC. Seeing in upright and inverted natural scenes. Journal of Vision, 3, 6, 440-455, http://journalofvision.org/3/6/5. Rousselet, G.A., Mace, M.J.M., Thorpe, S.J., and Faber. Thorpe, M. 2003, ERP Studies of Object Categorization in Natural Scenes, in Search for Category-Specific Differential Activities. Manuscript in preparation. Sajev, N., and Benton, S. 2001. Structural Encoding of Who? Man and Schematic Faces, Holistic and Part-Based Processes. Journal of Cognitive Neuroscience, 13, 7, 937. 951 PubMed. SCHYNS, PG, Jensch, I, Johnson, M, Schweinberger, S. R, and Goslin, F. 2003. A Principled Method for Determining the Functionality of ERP Components. Neuro Report, 14, 13, 1665-1669. PubMed. Severac-Cockhill, A., Edmonds, G.E., and Taylor, M.J. 2000. Is the face-sensitive N170 the only ERP not AF affected by selective attention? Neuro Report, 11, 10, 2167. 2171 PubMed. Tanaka, J.W. 2001. The Entry Point of Face Recognition. Evidence for Face Expertise. Journal of Experimental Psychology, General, 130, 534-543. PubMed. Taylor, M.J., Edmonds, G.E., McCarthy, G., and Allison, T. 2001. Eyes first. Eye processing develops before face. Processing in children. Neuro Report, 12, 8, 1671-1676. PubMed. Thorpe, S., Fies, D., and Marlett, C. 1996. Speed of process. Ing in the human visual system. Nature, 381, 6582. 520-522. PubMed. Van Rullen, R., and Thorpe, S.J. 2001. The Time Course of Visual Processing, from Early Perception to Decision Making. Journal of Cognitive Neuroscience, 13, 4, 454. 461 PubMed. Watanabe, S., Kakaji, R., and Puce, A. 2003. The Spatio-Temporal Dynamics of the Face Inversion Effect, A. Magneto and Electroencephalographic Study. Neuro. Science, 116, 879-895. PubMed. DOI 10.1167/3.6.5. PubMed article.